Yeah, can you explain again how you got x1 to be 2 over 5? X2 to be 4 over 3?
Okay, so one thing I just realized, so the reason x2 should be 8 over 5 is once we update the equation, then x2's value will change. But x1's values will be 2 or 5 because once we solve this equation here, we're basically setting x3 is equal to 0, x4 is equal to 0. So we're basically both of these are in the non-basic set. And then once we have 5/3 x1 to the 2/3 here. So you multiply by 3/5 and you get 2 over 5.
Question about the first thing, because it was x1 is 2 over 5. He was 4.
It was 4 over 3, but then I forgot one step. So the one step I skipped at the end is actually important. So once we update the other equation with that new answer for x1, it's actually going to change the value for x2.
Plug it back in.
Exactly. Yeah. So I'm gonna send an email to Claire. I realized that like literally 5 seconds
Because
after.
when you wrote both, so I went back to the first one. I was like, okay, or is it the first equation we solved for was 3 over 4?
Yeah.
So I wasn't sure how it.
Yeah. Hey, we
Plug it
need to
in.
adjust that. So I'll send an email about that.
Yeah. Okay.
I realized it right when I'm like, the one thing I skipped. I saw the time and I didn't want to keep people any longer, so that's why I kind of rushed it. But
Then I'm gonna try to finish the final. Oh, you're in Thursday? Well, I'm gonna probably do it tomorrow. Thursday. Oh, my buddy's house. Might as well, yeah. Been seeing him forever. Yeah. Oh, really? Oh, it's a clean up front. I haven't. Just the one. It's pretty busy today. Okay, we did it.
yeah, and Christine. So there's one step I forgot at the end of that example. So once you plug in that updated value for x1 back into the other equations, then you should get x2 is equal to 8 over 5. So the one part that I skipped, I was kind of rushing at the end just to kind of make sure everyone can get out in time. But I'm gonna send an email to everyone just to clarify. Thanks for catching that.
Jay, this would confuse me. You should have, you should have fall asleep. It depends on what I've done earlier in the day. So my internal old man has to regulate his rhythm.
Next thing you're gonna say is I'm like, how much question?
Dude, butterscotch?
It's too late. It's too late already. You start carrying around the random candies and go ahead and store it in my backpack.
The old lady, strawberry candies. You know what I'm talking about?
No, it's weird.
Yeah. No, I don't want to butterscotch. I could do that down to 19. It's been sitting there for so long. It's because all these fill out. They just. Tuesdays.
Wait, I'm gonna write in like I gotta do it from. I haven't done my transfer program. Huh?
Do you think
My transfer requirements. I really should be. I haven't done them. I haven't logged anything. I've done shit, but I just haven't.
But
So I just gotta look at the activities.
oh, yeah, they might see, like, they might see it not hold on to the clock. Yeah, like, it's, you do have. I'm gonna pick up on. The college. Or just doing it after the fact, like.
I think this was. Office hours count comes out when all did some. I'm probably gonna do complicated things.
Yeah, what is that?
Transfer in.
You feel like hours?
Activities. Sessions, office hours.
Just go say hi to Mayor. People are looking at it, so. Is June saying we're probably.
Set a block, check it off, because I've just been.
All right, it's 5:30, so let's go and get started. All right, good evening, everyone. How's everyone doing today?
All tennis.
Good, doing good. All right, so it's week 7. So you know, we are definitely gonna take it now. So I'm sure you guys have midterms and stuff, and so I know there's a career fair coming up in a couple of weeks too, so you guys are really busy. So you know, I always say I always appreciate you guys coming to class. Especially when they're recorded and stuff. I know it's kind of easy to view the recordings later, but you know, I appreciate not having to talk to an empty room. That's always which I'll do, but it's not pleasant. It's not as nice as talking to a. Okay, so the plan for today is we're just going to continue where we left off, and so we have a bit more to talk about in terms of shell and beam elements, and so we kind of introduced the concept of that last Thursday. And then, but today we're actually going to talk about how do you actually create these enhances and what operations that you're going to do. Okay, all this is set up for our ANSYS activity on Thursday. Okay, and so Thursday's ANSYS activity is going to be the last one for a while, and so I wanted to get this one in before before the midterm project, because some of you may want to apply shell and beam elements towards your midterm project. And in fact, there is one geometry among the choices where I think shell and beam elements would be fantastic for. And so, I wanted to get activity 4 in there before the midterm project, but then after activity 4, we are going to take a break. And so just to give you guys a chance to work on the midterm project and kind of focus on that, we're not going to do another ANSYS activity until basically close to Thanksgiving. Okay. And so, that's kind of the plan today. Okay. And so in the meantime, since we're not really going to be touching ANSYS in class, we're going to take this time to kind of start talking about some of the theory behind FEA as well. Okay. And so, because of the nature of this course, this course isn't strictly supposed to just be an ANSYS course. We do need to learn some theory, just because I know some of you will on and kind of take more advanced courses in FEA, or maybe some of you will go and develop FEA code. You should have at least a basic understanding of kind of the stiffness matrices and the assemblies and the elements, kind of how all that kind of fits together on a theoretical view. And so that's kind of what the plan is going to be over the next 3 weeks as we cover that. Okay. All right. So question in the chat. Question: was the lecture from last Thursday posted? I know I uploaded to YouTube, but I might have forgotten to post it on the Canvas site. So I'm gonna double check that once I get back to my office. But yeah, thanks for checking out. Okay. Any other questions I can answer before we get started for today? Okay. All right. So let's go ahead and continue where we left off. And so let's talk about shell and beam elements. Specifically, let's talk about them in general first. We'll get into more specifics. Okay. So shell and beam elements are these specialized element types that you can use in a lot of FEA software, and including ANSYS. Okay? And their whole idea is to kind of give you a better option when you have challenging aspects of your geometry. Okay? In particular, the types of challenging geometries that I have in mind are geometries that are either very thin or very slender. And so what's the issue with thin and slender geometries, right? So last time, what we talked about was that we have this kind of almost like a pseudo rule of having multiple elements through the thickness. And so you should never have a situation where you have a geometry that's so kind of thin that you only have one element through that thickness. Okay? And so we did part of the visualization that we did last time is if we had a very thin plate. So a plate that's much thinner than it is wide or long. Okay. You don't want to have a situation where you only give it a certain mesh size, that your mesh kind of looks like this. Okay. And so if your mesh looks like this, then the way that we describe this is that we only have one element through that thickness. So we don't want this. Okay? Because what we discussed was that, in this situation, all of the nodes of the elements are sitting on the exterior of the geometry, right? And so that means that their solution is going to be, very heavily influenced by the boundary condition. Another way that we can describe it is that we don't have any internal nodes for this type of geometry. Okay. All right. And so to alleviate this, and so what I'm telling you here is that this mesh is too coarse, right? And so if you refine the mesh, and so if you decrease the element size, it is possible to decrease it enough so that you get some elements to the thickness. Okay. But a lot of times, your geometry can be so thin that this may not be practical. And so we ran a little bit of the numbers of that last time. So if you have a situation where your length is a certain ratio of the thickness, you may end up with a mesh of 4 million elements for just a very kind of simple plate, just to get that 5 elements through the thickness. 5 is a little bit overkill. Usually you don't need 5. So usually 2 or 3 or 4 elements is usually okay. And so in these situations where it's kind of impractical to use solid elements, you can instead use shell or beam elements, which are much better suited to these geometries. And so what we'll talk about today, first of all, we'll talk about how to actually create shell and beam elements, because there is a process in which you have to follow. It's not quite as simple as kind of the meshing that we've done so far, because you actually have to modify the geometry itself. Okay, so we'll talk about that process today, and then we'll talk a bit about what the convergence properties are like, and so how much accuracy and how much cost are you saving by using the shell and beam elements. Okay. That was just kind of a recap from last time. Are there any questions on this? Okay. All right. So let's jump into it. So let's talk about shell elements first. Those ones are actually a little bit more complicated. Let's talk about beam elements. Okay. So shell elements, and so shell elements are kind of your just as the name kind of implies, is an element that's very thin, like a shell. Okay. These are essentially 2D elements. They're 2D elements, but essentially we apply them in 3-dimensional space. And their main purpose is to represent geometries that are very, very thin. And so they have one length dimension that's much, much smaller than the other dimensions of the So the big difference, the thing that shells do differently is that, when you have that kind of very, very small thickness, okay, instead of representing that geometrically, so instead of representing that kind of truly as a 3-dimensional object in the CAD, we instead represent that thickness as a numerical property. Let me show you what I mean by that. So normally, you have a thin geometry, something like this. Right, so this part is fully three-dimensional. It's just very thin. And so when we turn this into a shell, well, actually, let me first say. So let's say that this geometry has a thickness of, I don't know, let's say 3 millimeters. So very thin. And so if we were to represent this as a shell element, visually what you would see is that it would basically almost look like you took this geometry and replaced it with a piece of paper. So one that's kind of very, very thin. Okay. And so it would look something like this. We have basically a two-dimensional object. Okay. And so obviously when you kind of reduce it into a two-dimensional object, you don't see that thickness anymore, right? So that thickness of 3 millimeters visually is gone, geometrically is gone. Okay. But it still saves that information. So when you transform a geometry into a shell element like this, it saves the thickness information, but it kind of almost saves it as a material part. So in this material, we store information, what's things like the Young's modulus, we store things like the density, Poisson's ratio, okay? So all these are numerical values that are stored, within the geometry itself, okay? Not explicitly, right? It's just kind of stored in as a number. And so when you turn a geometry into a shell like this, we kind of basically add one more property for the thickness. And so instead of kind of representing the thickness kind of geometrically or visually like above, it's instead stored as kind of almost like a material part, like a number that the geometry knows is there. It just doesn't represent it like. And so if you think back to activity 3, actually, so that strip that we used to apply that wind force on the side, that was essentially a shell model, right? And so that was a shell model that we applied. We kind of stuck it to the end of the signpost. And remember, one step that we did was we kind of manually assigned the thickness of that shell. Okay. At that time, we assigned the thickness to be very, very small because we didn't want it to affect kind of the structural properties of the signpost. But in theory, you can set that thickness to be kind of whatever you want to represent that shell. Okay. All right, and so we'll talk about kind of how we can assign that thickness because there are kind of multiple ways to do this with it. Okay, so let's talk about the different methods of creating shells within ANSYS. So there are four methods. We're only going to use one of them, but it's useful to know kind of the others how to be. Okay. So the first method is probably the most manual of methods, and so this involves using the CAD tools within ANSYS. And so one way is we can create a 2D sketch. And we can assign it to be a shell surface. Right, so when you create a sketch, it's naturally a 2D object, and so we can assign that to be, we can just make that a shell just from there, okay? And so if you're creating your geometry from scratch within ANSYS, kind of like what we did in activity 1, that's going to be a viable option. Okay. So is number 2. It's number 2, another way to create a shell within ANSYS is to create an open sketch. And so an open sketch, it may be one that doesn't have a closed closed boundary. And so we can create an open sketch and use some CAD tools like extrude, revolve, or sweep to generate a planar surface. So I believe you can do these two operations in SolidWorks as well. I've not tried it myself, or not in a very long time, but in theory, operations 1 and 2 here are kind of basic CAD operations. And so they should be available within SolidWorks or Autodesk Inventor or CATIA or whatever your CAD software of choice is. Okay. And so if you're creating a geometry from scratch with the intent of certain aspects being shells, options 1 and 2 here are kind of perfect for that. Okay. But a lot of times, you don't have that luxury. So, and what I mean by that is that, usually you're working from a CAD file that was either given to you and you don't really have the means to modify it, or you don't have kind of the time to modify it. And so you're going to have to basically turn an existing CAD model into shells and beams. So option 3 here is for that. Option 3, there is a tool within ANSYS called the mid-surface tool. Using the mid-surface tool to extract a shell from a thin part of existing solid line. So that's the main one that we're going to use, and we're going to make liberal use of that in activity 4 on Thursday. Okay. Then option 4. Option 4 also works for an existing CAD file. It's just a little bit more niche. Okay. And so option 4 here is to use another tool. And so option 4 is to use a tool called the thin/surface tool. And the idea is to extract a shell of an otherwise solid object. So we're not really going to talk about options or method 1 and 2, just because that kind of requires you to have control over your CAD file and kind of create it from scratch. And so we're going to focus mostly on 3. We'll talk a little bit about 4. We're not going to use it in activity 4, but we'll definitely talk. We'll mention it just because it can be used in some situations. Okay. All right. So let's talk about method 3, mid-surface operation. And so the idea with the mid surface is that, in your existing CAD file, if you have a thin part of your geometry, you should be able to identify two sets of parallel or a set of parallel surfaces that are very close to each other, right? And so the whole idea is that, when you can identify that, if you have two kind of planar surfaces that are very close and very parallel to each other, then if you replace that with a plane, then that's kind of right in the middle of those, that plane will then become your shell. That's an explanation. So let me write that down. So the idea is to replace two parallel Hence the name mid surface. So we're literally creating a new surface in the middle of two existing surfaces. Okay, so let me kind of show it visually first, and then talk about how it actually. So let's say that you have a part of your geometry that looks something like this. Okay. And so we have a part where we have kind of two planes here that are almost parallel. That they are parallel. And so if we look at this surface right here, let me call this, we'll call this surface 1. And if we look on the back side, so on the back side, we have another surface, or we have another plane that's kind of parallel to 1. And we'll call that surface 2. When we perform a mid-surface operation, what it's going to do is that it's going to eliminate the thickness of this part here and replace it with just a thin slice. Okay. And so it looks something like this. So instead of having kind of a block with thickness here, you're going to have a slice that looks like, where the original geometry, would look something kind of like. So in red, and you'll actually be able to see that. And so when we do mid-surface operations in activity 4 on Thursday, what you'll see is that once you create a mid-surface, you'll kind of very briefly see the original geometry that was there, and you'll see the new mid-surface that you create is going to be literally right in between. And so this new plane here created. This new plane here is now a shell geometry. And when you mesh it, it's going to create a shell mesh with shell elements. Okay. And so when you create a surface using the mid-surface operation, the thickness of that shell is automatically recorded. Okay? Because when you do a mid-surface, ANSYS automatically records, what the distance was in between your two parallel surfaces. Okay? So this distance right here would be the thickness. And so that's going to be automatically saved into your part. So you don't have to enter the thickness manually. ANSYS will kind of determine that automatically. thickness is automatically recorded. All right, so that's the primary method. So that's what we're going to do in activity 4 on. All right, any questions on the mid-surface operation? All right. So let's talk about the hollowing out. And so let's talk about the thin surface operation. So we're not going to do this one on Thursday just because it's a little bit more niche, but it's good to kind of know. Okay. So the basic idea behind this operation is that you start with a solid object that has a thickness, and so this may not be a thin geometry itself. Right, so this can be anything. And so the idea with this operation is to hollow it out. So it's almost as if you kind of almost spray painted the outside and just extracted just that layer of spray paint, and that's going to be your object. That's going to be your shell. Okay. In fact, one thing that you can do, just to kind of make it a little bit easier to work with, is you can actually remove an exterior surface as well. Okay, so I think kind of the simplest way to kind of illustrate this is with a cube. So let's see, so right here we have kind of a pure solid cube. Here soon by magic. Once the internet kind of catches up. There we go. Hey, all right. Okay, so pure solid cube. Okay, so no shell, no anything, and it's too thick to become a shell through a mid surface. Okay, but maybe we want to kind of just hollow this out. So maybe instead of a cube, we want to get the box that's just surrounding, like an empty box. Okay, and so what we can do, we can take our cube again. And so the way the thin surface operation works is that you're going to choose one surface when we model. Let's say that we choose the top surface here. Okay. This surface is then removed. And the entire interior is basically gutted. So we don't have any more interior. And then all the other remaining surfaces on the solid they basically become shell surfaces. And so it's basically like you have an empty box. Okay. An empty box without a lid. And so with this operation, we're not, ANSYS doesn't have any information about the thickness. And so this would be a case where you'd have to assign the thickness manually afterwards, basically in the same as activity 3, okay? But if you use a mid-surface operation, then ANSYS kind of knows already what the thickness is, and then there's no need to assign it, okay? And so kind of the important thing to kind of remember is to, whenever you're using ANSYS, keep an eye out for those kind of blue question marks. And so whenever you have a blue question mark, that tells you that ANSYS wants you to assign something before you move on. Okay. All right, any questions on this? Okay, all right, so that's everything with shells. Let's talk about beam elements. All right, and so a beam element is a 1D element or a 1D, geometry that's used to represent slender parts of the geometry. So because they're one dimension, that means they're very, very cheap. Okay. And so 1D elements, we haven't really talked about them yet. We'll talk about them soon once we go over the theory. Basically, the idea with 1D elements is that they either have 2 nodes if they're a linear element, or 3 nodes if they're quadratic. So very cheap. But because they're basically a 1D representation of a 3D geometry. Okay? It has to kind of store more information internally, more so than the thickness. Okay. So internally, a beam element needs knowledge of not only its thickness, okay, but it needs information about its 2-dimensional cross section. Okay. Cross-sectional area and cross-sectional shape. If you think about it, when you're creating a shell element, you're only compressing one dimension of the geometry, right? And so that one dimension is represented by a thickness. Okay. When you're creating a beam element, you're basically compressing a 3-dimensional object into a 1-dimensional object, and so you need to store 2 dimensions worth of information internally. Okay. Let me kind of illustrate to you kind of what the issue is. So, in the simplest case, maybe you have a cylindrical rod here. When you represent this with a beam element, it just looks like a line. Let me give you another example. So let's say that we have an L bracket or an L beam. So exact same length, and so exact same length of the cylindrical rod from above, okay? When you represent that with the beam element, you lose that information, or you lose that kind of dimension for the cross section. And so when you represent it as a beam element, it becomes a line. Let's look at an I beam. So same thing here. And so, in 3 dimensions, you can actually view, the I cross section, okay? But when you transform it into a beam element, it becomes a line. So all 3 of these examples here, they all are represented in the same way as a beam element, at least visually, right? So visually, they all get transformed in just a one-dimensional line. But we know, just intuitively, that all 3 of these beams are going to have different performances and different types of properties when you actually put them in a structure. Okay, and so to kind of respect this and to kind of encapsulate this information, a beam element needs to know what its original cross-sectional area was. And so internally, a beam element is actually a little bit more complex than a shell, because a shell, you basically only add one material property. You only add the thickness of the shell. But for a beam, it actually, the way it stores is actually very interesting, because it actually stores a sketch, a 2D sketch of what its cross section looks like, and that sketch kind of has a dimensions and everything. And you can even modify the sketch so that it's off center, rotated, and things like that. So of course, that's only relevant, if you're creating a beam from scratch. But there's kind of an easy way to create a beam where this is saved automatically. And so just like the shells, there are multiple ways to create a beam, and we'll talk about just 2 of them. And so I'm mentioning in ANSYS here, but these methods should apply to other softwares as well. All right, and so the first way that we'll talk about is kind of a more manual approach. And so this is kind of, again, if you're kind of creating your CAD from scratch within ANSYS, you can use this method. And so that would be to create a 1D line sketch. And so you would go into the CAD software, whether it be Design Modeler or whether it be Space Claim. And so we'll get to use Space Claim on Thursday. And so you're going to create a line, you're going to sketch a line, and then from there, you're going to manually assign it its beam properties. So that actually means, sketching out its cross section and dimensioning it and kind of storing that information within the. Okay. Right. So that's great. So again, that's great if you're creating your CAD from scratch. But a lot of times, you're not given that opportunity because as a finite element analyst, usually you're given the CAD model that was created somewhere else. Okay. And so the second way of creating a beam is to kind of do it in kind of a similar fashion as the mid-surface. Okay. Instead of mid-surfacing, we call it an extraction operation. The name of the tool is actually called extract. What you're going to do is you're going to extract slender parts of the geometry into some beams. Of course, the second one is what we're doing. Okay, and so we're not really going to discuss method one, you know, just because that's just not what the activity is going to be. But you know, I will say this, and this goes for the shell elements too. That you know, even though it seems like kind of a hassle to create these from scratch from your CAD model, that actually kind of gives you the more stable result. And so if you can create your CAD model from the beginning with the intent that you know you're going to use shell and beam elements inside the analysis, that's going to create a much more kind of stable you know, geometry with a lot less cleanup that you have to do. So you know, all of this sounds great today, and you know, I always tell people that you know after I give the lecture on shell and beam elements, everyone's kind of really excited to use them, and so they're like, yeah, shell and beam elements is great. And you actually go to try it, and then after activity 4, you're like, shell and beam elements suck. You know, I don't want to use these ever again, because you know, even though it sounds simple to use the mid surface and the extract, it actually kind of messes up your geometry to a certain extent. And so we're actually gonna spend a lot of time cleaning it up after. Okay. And you'll kind of get what I mean on first. Okay. And so how do we extract a geometry? Okay. All right. So the way this works actually, you know, mechanically is actually very easy. And so all you need to do is if you have an existing CAD file, from an existing CAD geometry, what you're going to do is that you're going to just click on the parts that are slanted. That's it. And then after you click on it, then ANSYS will automatically convert it into a beam. Okay, so let's say that you have a part of your geometry. So let's say that we have a rectangular cross section like this. Okay. When you use the extract tool, all you have to do is just kind of point and click to that area. And then voila, you have a beam element just like that. Okay. And the best part about this is that when you use the extract tool like this, you know, very similar to the mid-surface operation, ANSYS will save all of the internal information that it needs. Okay. Because visually, you know, you can see what the cross-sectional area looks like here. Okay. And when you click the extract operation, ANSYS will automatically save that cross-sectional shape into the beam element. So that's great. So the extract tool is very easiest to do. It'll probably be your favorite part of the activity. You know, just clicking on parts of your geometry and making it turn into. All right. Any questions on beam so far? All right, so then what's the issue, right? And so, we went over, the mid-surface operation. That seems relatively straightforward. You just identify two parallel surfaces. And you create a shell in between them. We've gone over the extraction operation. It's just a point and click. And so, what could possibly go wrong? So this all seems kind of very straightforward. Well, the issue is when you have an existing CAD file, all the dimensions and all of the all the sizing for all the parts assumes that you have a fully three-dimensional model. And so, your original CAD model here was designed to be fully three dimensions, right? And so all the parts are connected under the assumption that everything has a full thickness. Okay. And same thing for the beams. And so when you start to use mid-surface operations and extract operations, you kind of eliminate a lot of that thickness. Okay. It should be pretty negligible, right? Because the idea is that you're using the mid-surface operation on parts that are already thin, but it's not negligibly thin. So there is still some thickness. Okay? And so what tends to happen is that as you create more mid-surfaces and as you create more beams, it's going to create gaps in your model. And gaps can be a very, very big issue because, because in reality, there are no gaps. So there's no gaps in your model at all. And so this could create issues in terms of the connections. And so you're going to have parts that are just kind of floating relative to each other, even though they're supposed to be attached. It's going to create issues with, sliding between parts. And so that's now going to be possible as well. And it's going to create a lot of contact issues as well. So let me kind of give you an example. So let's say that you have a geometry that looks like this. So you have a fairly thick part here, and we have a fairly thin part on. So this could be like a tabletop, okay? So for a kitchen or something like that. Okay. And so we look at this geometry. We say that okay, the top of this geometry here is very thin. So let's go ahead and replace this with a shell. And then the operation that we're going to use is going to use a mid-surface operation. So we're going to leave the base alone. So the base is still going to be the same. So we're going to have the base. But turning that top surface into a shell. Draw kind of the original geometry. So that's great. And so, we've taken a thin part of our geometry, we've converted into a shell, just like we're supposed to, right? And so once we mesh this, we're going to be able to use our 2D shell elements, and it's going to be a lot more efficient than before. The issue now is that now our tabletop is floating, right? So now we have a gap in between these two parts of the geometry that were originally connected. And so before we actually move on to the finite element simulation, so before we actually move on to the finite element simulation, we need to address this gap. Because if we were to import this directly into ANSYS Mechanical, then ANSYS is gonna recognize that as a gap, and then once you apply forces, this tabletop is going to slide right off. And so we're gonna be doing a large combination of different procedures. And so we're gonna be moving some parts, we're gonna be extending some parts, all basically just to make sure that we cover all the gaps that shouldn't be there. And you'll be surprised. There's going to be a lot of gaps to cover. And in fact, I think activity 4 is probably the most challenging in terms of just the amount of time it takes to do all. And so Thursday's going to be pretty packed. And so if you're going to show up for one ANSYS activity this semester, I would do it for activity 4, just because people are going to run it. You're going to run into issues with it, and it really helps if I'm kind of there to kind of walk you through. All right, but we'll get more into that on Thursday. That's a little bit harder. All right, any questions on this? Okay, so very quickly, I think we'll save the stiffness method for next time. But let's very quickly kind of talk about the accuracy and convergence of shell and feed. So this is the whole reason, why we bother with shell and beam elements, right? So the whole idea is to kind of help us converge on a solution in a lot less elements than it would be solid elements. Not only are the elements that we're going to use for shells and beams, each element there is cheaper just because we have a lot less number of nodes, but they just have way better properties in terms of solution. Okay. And so if we were to plot, we have kind of a typical kind of mesh convergence plot. So on the horizontal axis, we have the number of elements. On the vertical axis right here, we have the solution value. So the solution value could be anything that you extract from the finite element solution. And so most of the time we use stress here, but sometimes you can use deformation as well. Okay. And so the idea is that as the number of elements increase, we're gonna get closer to the true solution. Okay. Let me kind of draw a dotted line right here. So this dotted line right here will be like the true solution. So if we were to use solid elements, maybe it looks something like this. And of course, so this plot right here is assuming that we have thin and slender parts of our geometry. And so this would be kind of a textbook case in which you would want to use shells and beams, okay? And so, you wouldn't use shells and beams in cases where, you don't have thin and slender geometry. So it's kind of assuming that, you have. And so we use solid elements, what I would say is that, you would reach convergence kind of somewhere around here. And if you look at the position of where we are on the horizontal axis, that's really far to the right. And so, what this is basically telling you is that if you use solid elements on a case where you have a thin and slender geometry, it takes a lot of elements in order to get convergence, okay? And so remember what we talked about last Thursday, that, if you have thin and cylinder geometries, it is possible to get convergence with the solid elements. Okay, so with your usual tetrahedrons and hexahedrons, it's just going to take you forever to get there. And a lot of times it's just not going to be practical. On the other hand, if you were to use, shell and beam elements, your convergence might look something like this. Green right here, we have shell. And so if you look at the point in which it kind of reaches that convergent point, it's approximately kind of right there. Here we have so if you look at where we are on the horizontal axis, this occurs at a much earlier place. And in some cases, this improved convergence is actually even more dramatic. And so it's much less than kind of what. Question. So is this also why they cost less, because the convergence happens much sooner? Yes. And so this is actually the primary reason why they cost less. The whole game that you're playing with finite elements is that you want to get as accurate of a solution as possible using the least amount of elements, because the more elements that you use, that's going to add cost to your simulation, right? And so if you can get the same result or the same accuracy of result using a lot less elements and a lot less computational power, that's a big win. Okay, because in reality, if you have kind of infinite computational power, you can probably get a seventh grader to do finite element analysis, right? Just tell them just mess the shit out of it, just give me like 500 million elements, and for sure you're going to get an accurate solution with 500 million elements. Okay. But then there's no skill involved in that. A lot of times people don't have access to that many computational resources, and so kind of what your role then is as a finite engineer is is to kind of do these kinds of techniques in terms of how can you get the same result or the same accuracy of result using a lot less work, using a lot less resources from the company. And that's kind of what gets you paid as a finite element. All right, and so that's kind of the big motivation of kind of why we do this, is to reduce the cost. All right, any questions on this here? Okay, all right, so let's end a little bit early today. So I did bring the other lecture notes for the stiffness method, but I think we have like 13 minutes left in class, and I don't want to just touch on it. We'll probably start it next week after the activity. Okay. All right, so Thursday is our next ANSYS activity, and so, you know, you definitely want to show up for this one. It's gonna be a long one. This is the longest activity that we have. And so I expect to kind of be running around, you know, the entire time. And in fact, you know, I think, you know, probably a lot of you are probably not gonna finish, the in-class portion. Just because it's a model. So this activity is a doozy, and so there's a lot. All right, so but thank you guys for coming today. I hope you guys enjoy the rest of your evening, and I will see you guys on Thursday. Right, so shell and beam elements have the same properties of the solid elements for lithium, and essentially without a dash. You can think of it that way, yeah. You do lose some information. So, you know, shell and beam elements are appropriate. And you are kind of making some sacrifices, but you know, for the majority of cases, if you have a part that's you know thin enough or sufficiently thin or sufficiently slender, you know, you're not really giving up too much, and in fact, is gaining a lot in terms of you know how much cost the thing is. Oh, yeah.
So I forgot to ask you this.
Didn't even look. But on.
Spines for it?
Yeah.
That could be on the six. Okay.
So it's only gonna go up to lower extremity.
Cool. Okay, so. Yeah, it said the. Spinal.
Oh, shoot, I forgot to take that off.
Yeah.
It should just be upper and lower extremity.
Okay, awesome.
Yeah, so you can roll, so 1 8.5 by measure sheet, so you can
Oh,
write
the full sheet?
a full sheet and both sides.
Oh, cool. Okay, awesome. That was. Good.
So the FE exam's interesting, so I've had friends that have taken it, I've had friends that have never taken it. I've never taken it personally myself.
Oh, really?
So it's.
I just haven't gone around because like shit's been happening. Gotta do this, gotta do X, Y, Z thing, you know?
Yeah, but what usually happens is, so most companies don't require it, but a lot of them are willing to give you. If you complete it and you pass it, because then you have more credibility. But it's a company by company basis, so.
Okay.
I have to ask kind of the company to do it. If they do require it, and if they do require, they'll usually say on the application. If they don't say that they don't require it. And if you do have it, then.
They raised, yeah. Not the first time that they're raised.
Oh, yeah.
Yeah.
Thanks for your help.
Yeah,
I'll see you tomorrow.
Yeah. All right, any other questions from Zoom before we wrap it up? I'll check and see if you're still in there. Okay, all right, I will see you guys on